So a few summary observations about permutation ellipses. Defined that on this 2020 paper by Kimberling and Moses. The idea here again is you take a triangle ABC, you elect some fixed point P on its plane with barycentric coordinates P, Q, and R. You permute them and you get 6 points that lie on an ellipse centered on the barycenter and homothetic to the Steiner circumellipse of ABC. I was speaking with Bernard Gibert today, and he told me he has a paper from 2002 called Tucker cubics and bicentric cubics. I'm going to leave a link in the description. And the same concept is described there all the way back in 2002. So namely, he'll define a point P, P, Q, R, and he will first define 3 points with certain permutations. Let's see, where are they? These are not it. The points are these here, over here. P sub P, P sub Q, P sub R. Okay, and then he's going to define, so these are permutations of P, Q1 and Q2, also permutations of P, and then he calls a certain object a bicentric conic, okay, and he's going to say the 6 points P, Q1, Q2, P sub P, P sub Q, P sub R, the 5 permutations, all lie on an ellipse E1 centered at G and homothetic to the Steiner circumellipse, and there's an equation here. So let me go back to GeoGebra, and I want to link this with a conversation I had with him today. And okay, so first of all, let me talk about a couple of results, and let's actually recap what this construction is all about, right? I have a triangle ABC. I'm going to elect a point P, and in this case, I'm going to constrain P to be on the circumcircle. Then I'm going to apply the 5 permutations to the barycentrics of P, as described by Gibert on his 2002 paper, and also by Kimberling and Moses in the 2020 paper, right? So I'm going to go ahead and permute the barycentrics of P. P now is constrained to be on the circle of ABC, and I'm going to obtain these 4 permutations here. So I'm labeling them arbitrarily. So let's start with P2 is over here, P3 is over here, P4 is over there, P5 is over here, and P6 is over there. So there's all in all 5 permutations, and along with P on the circumcircle, I have 6 points that, per the 2 papers we just saw, must lie on a conic, this magenta conic here, which is a homotety of the Steiner circumellipse. So if I move P along the circumcircle, this magenta permutation conic varies, okay, and its center is always the barycenter of ABC. Again, this conic is a dilation of the Steiner circumellipse, so all of them are going to have a center on x2. So far nothing new here, right? Now what we did, I think on the first video, was to analyze what was happening to the locus of each one of these points, P2 through P6, these permutations, as P traversed the circumcircle. Why am I picking the circumcircle? Just because I thought it was an interesting locus to analyze this phenomenon by. And in fact, we're going to be talking about a couple of new observations here. So the first thing you observe, which we described in the previous video, video number 1, is that each one of these permutations follows a green path, which is an ellipse, and this happens to be a circumellipse of ABC. So the locus of each one of these permutations is a circumellipse. Note that the locus of P, the circumcircle, is also a circumellipse. So, with that idea, and actually speaking with my colleague, Professor Pedro Reutemann, he said, then can you check if there's anything interesting about the areas of these 5 circumellipses? And it turns out their 5 areas are the same as the area of the circumcircle. So we're looking here at the 5 green ellipses, circumellipses, which have the same area as the area of the circumcircle. So now you ask yourself, that's pretty cool, right? So let me actually just put this on hold for a minute. Let me talk about this red ellipse here in the middle. It turns out that the centers of the 5 green ellipses, which I'm showing here as O2, O3, O4, O5, and O6, they are conconic with the circumcenter. Okay, and they lie on this red conic here. Now it turns out, Peter Moses told me this, that this conic is also homothetic to the Steiner circumellipse. Okay, you can see here more or less, right, that if I place P on one of the vertices, I get the Steiner. So right now, the magenta permutation ellipse is the Steiner itself, right? So you can see here that the magenta and the red, they're both centered on X2 and they are homothetic. Okay, so thanks Peter Moses for calling this to my attention. And then I just played around and said, okay, let me take the barycentrics of X3, which are sine of 2A, sine of 2B, sine of 2C. Let me permute them 5 times, and let's see where the permutations fall. It turns out the permutations fall exactly on the centers of those 5 green circumellipses. So there's some major harmony going on here, right? Not only did we draw 5 circumellipses by sweeping the circumcircle with P, and then tracking the motion of the 5 permutations of P, which give us these 5 circumellipses, but also their centers are permutations of X3 itself. Okay, so the next question, and this is the other beautiful remark here, and I want to thank both Bernard Gibert for contributing an enormous sextic, which I'm going to be using here, and Peter Moses for giving me an implementation of the sextic here on GeoGebra or GeoGebra. So we can ask ourselves the following: if these 5 green circumellipses have the same area, and their area is the same area as the area of the circumcircle, I may ask something more generic about a triangle. What is the locus of the centers of circumellipses of a triangle ABC such that their area is the same as the area of the circumcircle? Right, so we have here 5 representatives of such circumellipses. Now, if you think about the space of circumellipses of a triangle, that's a 2-dimensional space. There's a 2-dimensional pencil of circumellipses to a triangle. How do I know that? Because their isogonal images are lines that do not intersect the circumcircle, and there's a 2-dimensional space of such lines. Okay, so there's a 2-dimensional space of circumcircles. If I impose the restriction that I want them to have an area equal to that of the circumcircle, it's a 1-dimensional, so this collapses to a 1-dimensional subspace. And then I can ask myself, what is the locus of the centers of those circumellipses? Right? Because once you define the center of a circumellipse, the ellipse itself is defined since it must pass through ABC. So again, this is a contribution by Bernard Gibert and Peter Moses. And this curve here, sort of curvy triangular curve, is actually it's an implicit on the barycentrics of a point in the plane of the triangle of 6th degree. So it's a sextic, right? It's a 6th degree curve. And beautifully, and as expected, it contains X3 by definition. Why? The circumellipse that is centered on X3 has the same area as a circumcircle. Why is that? Because that circumellipse is the circumcircle, right? So X3 must be on this orange curve. And then, as we just discussed experimentally, these 5 ellipses here, and this is not proved, but they have the same area, we just see this numerically, as the circumellipse itself, so they too must lie on this locus. Now, any other point on this orange locus here is going to give rise to a circumellipse of the same area as the circumcircle. So let me go ahead and move P here so we can see a little. Now what I can do here, and this is going to be risky because it takes a couple of seconds to compute this orange curve via GeoGebra, I'm going to move C around and to see how this curve is perturbed. So let's move C over here. GeoGebra is computing. Let's just wait here a couple of seconds. There you go. So I changed the triangle. You can see now that the geometry has changed slightly. This triangle is too close to being an isosceles triangle. And by the way, I think video number 2, I was just, being pretty foolish by saying, oh, what is the locus of C such that X3 is on that axis of the Steiner? Of course, the set of all isosceles triangles will have that kind of characteristic, and you get this sort of collapsing. But let's go ahead and move this to a non-isosceles configuration. And by the way, it's an interesting question, right? What is the shape of that sextic when a triangle is isosceles? So here's a non-isosceles triangle. You get a different sextic. Everything seems to continue to hold. GeoGebra did not properly compute this cusp here, but I think if I change the zoom, so I just asked it to recompute here with a bigger zoom. Let's see if it gives us a better picture of this sextic. Yeah, so you're going to get a cusp here, right? So one question we may ask is, what is this sextic if the triangle is, does that make any sense? Yeah, that could be a good question. If the triangle is equilateral, the sextic is going to be 3 curves. So does it collapse to a degree lower than 6 if the triangle is equilateral? What's the sextic if the triangle if the triangle is an isosceles, so forth and so on. But the cool result here is that it seems like everything is consistent. Using the permutation idea, if P slides over the circumcircle, you get 6 circumellipses, you get 5 circumellipses. They have the same area as a circumcircle. Their centers lie on a permutation conic, this red ellipse here, which passes through X3, and the permutations of X3 are precisely the centers of the 5 circumconics, the green ones. And then using the Gilbert sextic, we can get this curve here, this orange curve, which passes through these 6 points. Anyway, guys, this is it for this video. Thank you very much. Bye.